With partitioned matrices, we sometimes subdivide matrices into either blocks, or we can look at a matrix as being comprised of a bunch of rows, or we could look at a matrix as being comprised of a bunch of columns. It really depends on the orientation of the problem. But the idea is to look at a whole object, a whole thing, a whole rectangular array as a sum of its component parts. Right now what we want to look at is this matrix equation. And this matrix equation is comprised of the matrix A, and then we're looking for values of x1 through xn, so that after we multiply our matrix A times our vector x, we want to get this vector B. So when you multiply A times x, this is the result of that, because you remember from matrix multiplication, it's the row of matrix A times the column vector x. So when you take the first row of A and multiply by the column vector x, this would be the result. And if you take the second row of A and multiply by the column vector x, this is the result. And then this is, of course, the last row of matrix A times the column vector. And you can look at this sum, the first row of this sum and the second row of this sum and the mth row of this sum. Instead of looking at it as a bunch of rows, you can really look at it as a sum of columns. So that's how we're going to partition this sum. We can look at this as this sum is really a sum of this column vector and this second column vector and this nth column vector. And each of those column vectors are columns of the matrix A. So this first column vector is really the first column of A, the matrix A, times a constant. And this is really the second column of matrix A times this constant, x2. And this last entry here is really the nth column of matrix A times this constant n. So when you have constants times vectors and you have a sum of them, that's called a linear combination. So what we have on the left side is a linear combination of the columns of A, and on the right hand side we have the column vector B. So our conclusion when we look at this kind of equation is to say there's going to be a solution to the linear system. There will be a solution provided B is a linear combination of the columns of A. So we'll look at an example of that next. So let's look at this example where we write the column vector B as a linear combination of the columns of A. So this is really equivalent to solving the system, AX equal to B. And when we solve the system AX equal to B, what we saw a few moments ago is that's equivalent to solving, say, x1 A1 plus x2 A2 plus x3 A3 equal to B. In other words, we're trying to write B as a linear combination of the columns of A. So to do that, we're looking for constants x1, x2, x3, so that those constants times the columns of A is B. So to solve that linear system, you can use your calculator. In the notes, you can see I solved this in R. To solve this in R, you do need to define this RREF function. That function is not part of base R. I put the code for that function on Canvas. If you open up R and you copy and paste that code into R, then that defines the function. The code actually is the code for the function. That would define the function, and then you can call the function, which is RREF. So, assuming you've defined the matrix and the code to define the matrix, I called the matrix here, I called the matrix here the matrix AB. And remember, R is a case-sensitive language, so this, I defined it as capital A, lowercase b. You can define it however you want, and you can use your calculator to do this as well. But if you want to do it in R, just remember, again, R is case-sensitive, so whatever's capital letters and lowercase letters are distinct entities in R. So we can see the reduced row echelon form of that matrix, and that's given here. So let's interpret that now. Let's see what that means. So there's two non-zero rows here, and the second non-zero row, what does that mean? So we see the coefficients of x here. So what are the coefficients? What is this? How do we do this? So what we see is we would have x2, 1x2 plus 3x3 is equal to 2. So what that means is x2 is equal to 2 minus 3x3. So we can see x3 is a free variable. We can parameterize the solutions. There's infinitely many solutions here, and if we let x3 be t, then that means that x2 is going to be 2 minus 3t. The first row of the reduced row echelon form, we'll interpret that now. We have 1x1, 0x2, minus 2x3, that's equal to negative 3. We know that we've defined x3 to be t, so we see that x1 is negative 3 minus 2t. So our solution then is, for x, our x vector, it's negative 3 minus 2t, 2 minus 3t, and t. So for any t is any real number. So as a particular example of that, we could choose, so we could let t be equal to 1. So one specific solution to this, one particular linear combination of the columns of A that's equal to B, that one particular solution would be, say, let's see. Oh, this should have been plus, by the way. I'm just looking at it. Sorry, I just noticed it should have been negative 3 plus 2t. This should have been plus. Okay, so if t is equal to 1, then x1 would be negative 1, x2 would be also negative 1, and x3 would be 1. So what that means is we would have, how would we write B as a linear combination of the columns of A? We would have negative 1 times the first column of A. That's 0. Minus the second column of A, plus the third column of A, and that's equal to our column vector B. And is that true? Seems to be. Negative 1 minus 2 plus 4 really is 1. 1 plus 2 really is 3. And then negative 1 plus 3 really is 2. So that seems to work.